fluids. So we will start from that point onwards today. So as we were discussing, surface tension is the property of any liquid whereby its surface, which is a thin layer of liquid molecules, thin such that its thickness is of the order of magnitude of a few times the diameter of liquid molecules. So it's an extremely thin layer that we're talking about. So such a thin layer which bounds the liquid or separates the body of the liquid from the surrounding environment, like atmospheric air, or if the liquid is in gravity-free space of vacuum, then the body of the liquid is separated from the vacuum by a very thin layer of molecules like this, which is called the surface. Now, this layer has an elastic property. It is elastic and restorative in nature, and that is measured by the physical quantity which we call the surface tension. So let's begin today by understanding the surface tension as a physical parameter or as a material property. So we had understood through some everyday examples the evidence of the fact that the surface of a liquid indeed is elastic in nature, and it has this ability to apply restorative kind of forces and store potential energy as pressure is applied on it or whatever. Okay. So surface tension is a measure of a liquid surface's elasticity. Okay. It is a material property. For a given liquid. So first, let's understand about surface tension and force. So this force is basically as a result of the cohesive forces, that is attraction forces between light molecules. Acting tangentially on a surface. So that is the first way we can measure or define the parameter of surface tension. So surface tension, which we will denote with the symbol capital T, it is defined as tangential force per unit length. On a liquid surface. So imagine we have like a laminar flat surface, like the surface of liquid in a cylindrical container. Now, if you visualize, in that surface, there will be intermolecular attraction forces, which are acting, which are called the cohesive forces, which are acting between the liquid molecules on the surface, tangential to the surface. And that's what gives the surface its property of elasticity. So force per unit length is a material property of the liquid. So its value actually depends on the chemical composition of the liquid, the exact molecular structure and all that. So imagine this surface. Now if you take a top view of that surface, then along any imaginary line on the surface, there will be forces acting tangentially. Like imagine you have broken the surface, which is like a thin disk of liquid, into two halves. So one half is pulling on the other half with surface tensional force. So this surface tensional force per unit length is what is the surface tension. So it is this tangential force per unit length, or we can also write it as dF by dA, where dF is the tangential surface tensional force acting on a length element dl of the surface. So T is the surface tension. Okay, so from this now we can understand that surface tension has dimension of force per unit length, and surface tension is measured in Newton per meter, or more commonly it is measured in millinewtons per meter. So that is like a common unit of surface tension. So just make a note up to this point. The definition of surface tension in terms of this equation can be read like this, that surface tension equals to the tangential force per unit length acting in a liquid surface. Okay, so now let's just to get an idea, look at the values of some standard value surface tensions. You don't have to memorize these values or anything, but for example, you can see benzene, it has a surface tension of this much at 20 degrees C. Don't worry about the temperature coefficient. It tells you how the surface tension changes with change in temperature. Okay. So generally very small amount of change in surface tension, but it's in millinewtons per meter. So benzene is one liquid which is like familiar to you. Okay. Octanol, another similar kind of value you can see. Okay. You go down the list further, you can see more familiar liquids also of interest, like chloroform. This one has surface tension of similar value. Okay. Ethanol, water. Don't know where there is mercury in the list, but it has a pretty high value of surface tension. Toluene, something else you'll be familiar with. Okay, so see, these are some common values of surface tension as a material property. Mercury, here it is. Extremely high value of surface tension, you can see. One of only 2 or 3 known liquid metals, mercury, has a high value of surface tension. Okay. So now let's understand this application of surface tension as a force per unit length which is acting tangentially on a surface with an example. So last time we were talking about everyday examples. Yes, polar molecules can have tend to have higher amount of surface tension because of the nature of the the cohesive forces being stronger in polar molecules. But at the same time, you cannot draw direct comparison just on the basis of molecules being polar or having more density or less density and all that, because there are a variety of factors. Okay. So ultimately, we think of it as an empirically measured quantity, just like Young's modulus of elasticity or elastic strength or yield strength, etc., of materials, or temperature coefficient of thermal expansion or resistivity or thermal coefficient of thermal conductivity, etc. These are all material properties which are measured empirically from experimental data. Yeah. So now coming back to this force acting tangentially on a surface, let's look at that with an example. So last time we were talking about everyday examples of how there is evidence of this kind of restorative or elastic force that a surface of a liquid can apply, and using that force it can support very lightweight objects. So let's look at an example like that. Okay, a lightweight object supported by surface tensional force on a liquid surface. So imagine an example. This is actually an experiment you can carry out at home also. You take something like soap solution, like some ordinary detergent powder mixed in water, and create a solution out of it. and then you very gently place a thin metallic needle on the surface. You'll see that if you balance it gently enough, the weight of the needle gets balanced by surface tensional force, and you can actually support the needle without it sinking on the surface of the liquid. Okay. Whereas you know the density of the metal of your needle is quite a bit more than the density of any solution. So there's no chance that it is buoyant force that is keeping it. So if you try to place that same needle inside the water somewhere, you'll see it definitely sinks. And definitely when it's placed inside the needle, it's completely submerged. So there should be more buoyant force acting on it. So that is a clear evidence that the fact that a thin needle is actually at equilibrium on the surface of the liquid means that it's being supported by some other force and it is not buoyant force. Now, if you also observe it very carefully under a hand lens or something, you'll observe that the surface of liquid where the needle is present, it will get a bit bent like this. It will get contoured like this. It's like it's got dented a little bit. Okay. So a thin metallic needle, okay, or wire or something like that at equilibrium on a surface of something like soap solution. So now if I magnify that diagram many times, what I'll observe is that, let's say the needle is like a thin cylinder. I'm not really worried about the pointed end. I'm just talking about it like a, and the liquid surface where it is present slightly bent like this. It's slightly contoured like this. So if I further magnify this and now just look at the cross section. So magnified cross sectional view of it. Then what I'll observe is that the surface of the liquid where it is in contact with the needle bent like this. My diagram might be a little exaggerated, but it's definitely going to have some kind of contour like this. So what will happen is at the point of contact, or rather at the line of contact with the needle, if you draw tangent to the surface, that will be at some kind of angle to the horizontal. Okay, so there'll be a relationship between that angle and the physical properties. Okay. So if the needle's length is, let's say, 4 centimeters, calculate its mass given that surface tension of the liquid, let's say 250 millinewtons per meter for the given soap solution. And secondly, the angle made by the tangent to the surface with respect to horizontal, okay, at the point of contact is about 3.6 degrees. So based on this information, and acceleration due to gravity is 10 meters per second square. So based on this information, we have to calculate the mass of the given needle. So let's try out this question. So ultimately it becomes a question of application of Newton's laws. Okay. Length of the needle is given to us as 4 centimeters. So we'll use the definition that surface tension is equal to tangential force per unit length. We'll use this and we'll make an FBD and we'll balance the forces. We'll look at the equilibrium of forces acting on. Okay, so where the liquid is in contact with the needle at two positions on either side of it, okay, it will be in contact along a line, and the tangent to the surface of the liquid is basically that red dotted colored line that I've tried to draw over there. So that is making an angle theta, which is a small angle. So we'll have to use some kind of small angle approximation also. Okay. Okay, so let's check this out. Yeah, it will come in terms of pi because you'll have to convert the angle to radians and also use the small angle approximation. So again, if I make the free body diagram for a magnified cross-sectional view, so you'll see that there'll be surface tensional forces acting tangentially at the two sides like this. Something like this. Okay. So again, actually this angle theta should be a very small angle. In the diagram, it doesn't reflect that it's a very small angle. So these are our surface tensional forces. So if you see the top view of the needle, it's like a thin object like this. And these forces are actually the collection of all these surface tensional forces acting on either side, but they are not actually coplanar. They are like coming out of the plane a little bit. So if this is a force dF acting on a length dl, it's d times dl. So this is surface tension multiplied by length. This is surface tension multiplied by length of the needle. And these forces together are balancing the total weight. So as you can see, you have the simple equation 2 times this tangential surface tensional force times sine theta is equal to mg. So m is equal to 2 times TL sine theta divided by g. So that is 2 times. Now the surface tension was taken as 200 millinewtons. So in newtons per meter, it will be like this. The length was 4 centimeters. So in meters, it will become like this. Okay. Divided by 10 into sine theta. Now theta, which is 3.6 degrees, is how much? 3.6 into pi by 180. That's correct. So pi by 50 radians. So it's a small angle. So sine theta is approximately theta equal to pi by 50. So in milligrams, it would be something like this. Yeah, sure. I'll scroll up. Oh, sorry, I took the surface tension wrong. It's 250. I've taken it 200 in my solution. Sorry. So I'll have to make a correction. So this will become 4 pi by 5 into. Okay, so it's all right now, something like this. 125.6 milligrams, yes. Sorry, I had taken the wrong value of surface tension. I had taken it as 200 instead of 250. So I made that correction now. Anyhow, so hope the application of the question is clear. So this is an example of how surface tensional force can be used to balance the weight of a lightweight object like this. Okay, now let's move on to the next aspect of surface tension, or next associated property with surface tension. So as we can see, surface tension here is associated with a internal conservative force which is restorative in nature. So whenever we have a situation where there is internal conservative restorative force, naturally we have the some kind of potential energy associated with that system. Okay. Any system which has a conservative restorative force will have a position of stability where the force should be zero. Will have a stable equilibrium kind of position, and at that position the potential energy should be minimum. So first of all, we should be able to define some potential energy. So let's understand that. So using the work by energy kind of model for understanding this thing, understanding potential energy, that change in potential energy is work done by an external agent against the internal conservative force, or negative of work done by internal conservative force, that kind of definition. So using that, let's understand what is called surface energy, or the elastic potential energy associated with the surface. And from that, we will learn another way of interpreting the property of surface tension. So surface energy, or elastic potential energy of a surface, due to its property of surface tension. So here straight away we'll define the absolute energy of a surface as the work done by an external agent against the surface tensional forces, that is the internal conservative force. So against the internal conservative forces in configuring a surface. So if we have, a body of liquid such that its surface is negligible, and from that we rearrange it into such a system where there is a sizable amount of surface. So we have to do work as an external agent against the internal conservative forces, or against the restorative forces, which are the elastic property of that surface. So that work gets stored in the system as surface energy. So very clever way to visualize this situation is that if you think of an experiment like this, where you have some kind of materials which have high adhesive force with respect to some solution. So adhesive force is the force that acts between unlike molecules. Okay, so let's say we have two thin glass rods placed very close to each other, and now in between them we put a layer of droplets of some kind of solution which clings to the glass very efficiently. So there's high amount of adhesion or adhesive force between the glass molecules of the rods and the liquid molecules of whatever solution we have there. So again, soap solution would be an effective way. So two glass rods placed almost in contact, very close, and we have droplets of soap solution which has surface tension equal to T. So now we can see that given that the distance between the rods is negligible, so the droplets are of very small volume as such, and therefore of very small surface area. We can say we have hardly got any surface to begin with. But now keeping one of the rods stationary, if we gently pull out the other rod away from it, so as to so as to create a film of liquid, film of soap solution, then we would be expending some work in order to draw out this film of liquid, and that work would get stored in the surface of that film as surface potential energy. So suppose this rod is kept at rest, but this rod is very slowly moved by the action of an external force, so as to displace it through a distance s. So this external force will be doing work against the internal conservative surface tensional force which is acting. So a thin film of soap solution is slowly stretched out in this manner, and as a result of that, work done by this external force is stored as surface energy in it. Now one thing to be mindful here is that this film of soap solution actually has two surfaces, because compared to what we have defined as a surface, the film is far too thick. The film in macro sense might be very narrow, very thin. It might be of the order of microns, but compared to the thickness of a surface we have defined as a few times the molecular diameter of these fluid molecules, uh, it's far too thick. So it's more like a sheet of liquid, and the sheet of liquid is bound by two surfaces. So again, if we take a magnified cross-sectional view of it, it's like the glass rods. The cross-section would look like this, and the film of solution that we have placed in between will look like a sheet like this. Try and draw that better. So that sheet will not be exactly like a symmetrical, like a plane shape. It's slightly bent like this at the middle. So it's like you have a body of liquid, okay, bounded by two surfaces. Okay. So the surface tensional force which is acting will be acting tangentially like this. So back in that diagram above, you can see that this surface tensional force that is acting. So if the length of these rods is L each, you can see that the surface tensional force is surface tension into L. So therefore the external agent will have to apply a force that balances 2 times T into L, because it's moving very slowly, so its acceleration is tending to 0. So the work done by the external agent is this, so it just becomes this. Okay. So constant amount of force, the surface tensional force is not increasing or decreasing. So you are applying a constant force to keep gradually pulling out that rod from the first one and stretching out that film of liquid. So this is what is stored in the system as surface energy. Now notice that surface energy can be written as tension, surface tension times 2 times Ls, which is nothing but surface tension multiplied by total surface area, because remember there are two surfaces. So the total surface area is 2 times L into S. Okay. So this becomes an alternate way of understanding the behavior of surfaces in terms of surface energy and the property of surface tension. Surface tension, according to this, is equal to surface energy per unit surface area. That becomes an alternate definition of surface tension. Surface tension is a physical property or physical material property for any given liquid which equals to the surface energy per unit surface area. So that's an alternate way of describing the property of surface tension in terms of energy instead of in terms of internal conservative force or restorative cohesive force. Okay. So just have a go through this section and then we'll discuss more applications of this next. Okay, so now understanding this, that surface tension is actually surface energy per unit area, or that the surface energy is directly proportional to surface area. This gives us a way to understand a lot about the behavior of fluids in terms of how the surfaces appear, okay, or how surfaces get configured naturally. So the fact that surface energy is equal to a fixed material property multiplied by surface area. Okay, so in other words, because surface energy is directly proportional to surface area, so that is why the stable equilibrium position for any liquid surface is at a configuration where the surface area is the minimum possible. So that is the natural shape taken by any fluid body. It tries to minimize its surface area. So the most obvious example of this is that a volume of liquid in gravity-free space, in zero gravity environment, like outer space, okay, or inside an orbiting space station. So basically, there it's artificial zero gravity created by centrifugal force balancing gravitational force. So inside a satellite or a space station that is orbiting the Earth, it's not that objects are weightless because you're not at infinite distance from the Earth. Obviously, weight is less than on the surface, but it's not weightless. But it feels weightless because you're also orbiting in such a way that mv square by r is balanced by the gravitational force. Okay, so that's why the reference frame inside an orbiting spacecraft is such a non-inertial reference frame that in that reference frame all objects have an apparent weight of zero because the centrifugal force acting on them balances the gravitational force, and so it's like an artificial zero gravity environment. So in that environment also, if you have a volume of liquid, it will always arrange itself into a perfect sphere, because geometrically the sphere has that unique property of minimum surface area to volume ratio. So a volume of liquid in any zero gravity environment like this always naturally takes the shape of a perfect sphere. So liquid will just appear like a ball of liquid, instead of falling to the floor and sort of spreading out. In a zero gravity environment, liquid will naturally take a spherical shape. Okay, because the spherical shape has minimum surface area to volume ratio. So given volume of liquid will have its minimum surface area, that volume is arranged into a spherical shape. Another consequence of this is that same reason why droplets of liquid coming in contact naturally coalesce or combine into a single body of liquid and not vice versa. Whereas work has to be done, that is, mechanical energy needs to be expended to split the body of liquid into parts, into discrete individual parts of liquid. Some work has to be done or some mechanical energy has to be expended. So very common type of question based on this is doing this kind of energy calculation, that I want to split a single body of liquid I want to split a single body of liquid into smaller discrete parts. Certain amount of work has to be done. Okay, so let's look at an example like that. A spherical drop of liquid which has surface tension equal to T, let's say, and radius equal to R, has to be split into 1000 identical spherical droplets. Find the work that the external agent needs to do this split. Okay, so take the surface tension as, let's say, 120 millinewtons per meter, and the radius of the original droplet, let's take it to be 4 centimeters. So want to break it into tiny droplets of 1000 such droplets. Yes, Vinith, after completing this question, I will scroll back up. Okay. So you can write down those two examples later, or you can just understand them again and you can write them down later also. Okay, so let me do the calculation and verify, Naman. So first of all, we'll have to understand that the one droplet of radius r, when you split it into 1000 droplets, so obviously I'm not going to draw 1000 droplets, but so 1000 droplets of radius small r, let's say, and this one is of radius r. So volume conservation will tell you that each one will have a radius of r by 10. So your initial surface energy was surface tension into 4 pi r square, but your final surface energy will be surface tension into 1000 droplets of radius small r inch. Okay. And your work done by external agent will be equal to the increase in surface energy. Okay. So now substituting this information here, you can see that the final energy will become so will become 10 times 4 pi r square. Is that correct? Okay. So the final surface energy is becoming 10 times the initial surface energy. So the work done is delta U, that is going to be 9 times 4 pi r squared. So 36 pi into what was the radius? 4 centimeters, and surface tension was 120. Millinewtons per meter, so we'll have to convert it. So this will become our energy in joules, the work done in joules. 36 pi into 16 into 120 into 10 raised power minus 4 and minus 3, so minus 7. So whatever this comes out to be, this will be the work done in joules. So I'm getting this answer as about 3.62 into 10 raised power minus 3 joules. Just verify my calculation once. Anyhow, so hope the method is clear. So there is that little trick here of first conserving the total volume of liquid to figure out how much is the radius of each of the new droplets. And from that, you figure out that the surface area is increasing tenfold actually. You can see there's a huge increase in surface energy in terms of a percentage change. It's becoming 10 times what it was. So it's a 900% increase. Yeah, Kevin, I'll scroll up. This part, Kevin, the examples I gave, or even before that? Okay. Okay, so we're done with this.
Yes.
Okay, Kevin. So we come to now another very important derivation and concept related to surface tension. And this relates to further interesting properties of liquids, including capillary action and things like that. And that is the fact that when you have any sort of curved surface of liquid, particularly if you know it's a spherical surface, then there's a pressure difference across the spherical surface, such that always the concave side is having higher pressure compared to the convex side. Okay, so we can understand this by visualizing actually a spherical body of liquid in zero gravity free space. You just visualize that ball of liquid, you'll understand that the outer surface is like a thin membrane, which is kind of a little bit under tension because of the excess pressure inside, and that tension is keeping it intact because there's restorative force. So that gives us the idea of how to calculate the excess pressure. So this is a phenomena which we can just call as the concept of, or the phenomena of, excess pressure inside a spherical drop. So first let's begin by calculating this excess pressure inside a spherical drop, and then we can generalize it to the fact that any curved surface or any spherical surface will have a pressure difference across it. Okay. So as I was saying that if we just visualize a solid sphere of glass of fluid, so a spherical volume of fluid. Now that liquid has surface tension equal to T, and this has radius equal to R. Now that body of liquid is bounded by a spherical surface. So that spherical surface is like a thin shell of liquid molecules, and that acts like a sort of like an elastic membrane. So as it turns out, the pressure of the fluid inside is greater than the outer pressure. P will be greater than P naught, and this change in pressure will come out to be like this, 2T by R. There's a proof of this also, and we'll discuss that next. Okay. So this is the excess pressure. This is the excess pressure inside. And as you can see, it's inversely proportional to the radius. So the smaller the droplet or the smaller the volume of liquid in that sphere, the more the excess pressure inside. Okay. So this is a very interesting property that a fluid develops as a result of its surface. Now the proof of this is also interesting, and it's interesting in the way we apply mechanics to prove this pressure difference. And it's also interesting in how we apply calculus in coming up with this result. Okay. So let's understand the proof of this next. So for the proof, what we do is we imagine that we have broken this surface into two equal halves. So what we imagine that we have actually split this into two equal halves, and that to the spherical shell. So we are imagining that now we want to consider the forces that are acting on half of the spherical shell. It's like an open hemispherical shell like this that we are imagining, and we want to just show how that hemispherical shell is in equilibrium, show its equilibrium condition. Okay. So this is not a solid sphere anymore. We are just considering a free body diagram of half the spherical surface, or like basically a hemispherical shell of fluid. So what we'll understand is that the other half will be tangentially applying surface tensional forces like this. And that is what tells us that the internal pressure must be larger than the external pressure. That is what is creating this surface tensional force in the first place. So if we consider each of these as df on length element df on a length element dl, then okay. So this is surface tensional force on an element dl on the circumference. That thing. Okay. Now there'll also be force vectors because of internal pressure, which will be acting like this. So we consider an area dA. This force will be like internal pressure. Oh, sorry, let's write that as P. So write this as DF. The external one we'll write with the subscript. Okay, so this is PD. So these are the force vectors which are acting because of internal pressure. And finally, there is force because of external pressure, which is also acting normally at the outer surface. So these are force on normal force on surface element dA due to internal pressure. And likewise, we have again normal force on surface element dA due to external pressure. P0, whereas the internal pressure was P. So now again through another derivation as well as a logical method, we'll understand that if we integrate all these force vectors, okay, so the collection of that are acting on the length elements, which will give us a net surface tension vectors acting from inside, radially outwards or normally on this, will create a force, net force due to internal pressure like this, and the outer ones will create a net force due to external pressure, and they will be like this in direction. Okay. So each of these forces, they are the net force due to surface tension. Okay. So that will be surface tension into 2 pi r. That's very easy to understand because all of them are acting parallelly in the tangential direction. So dl integrated over that full circumference gives us 2 pi r. Okay. And F is the net force due to internal pressure. Now this is the one that we'll have to show by another separate derivation, that it will be equal to P into pi r square. Now it's very obvious that it should be less than P into 2 pi r square, because total surface area is 2 pi r square. But as you can see, the vectors are radially outwards. So it's only a component of them which are adding. Okay. And likewise, F0 is the net force due to external pressure. Okay. And that F0 will be opposite in direction, but it will have the same kind of thing. Okay. So we will prove this also why it is this way. Okay. But now when you look at equilibrium, now you can understand the equilibrium condition will come from the fact that surface tensional force plus force due to external pressure has to be balanced with force due to internal pressure. So, okay. So 2 pi r into surface tension will be this pressure difference into pi r square. So I'll come to why this is pi r square exactly. Okay, but from, if you just remember, and I'll give you a shortcut way to remember this also, that why it's exactly pi r square. But from here we can see that the pressure difference comes out to be 2t by r. So as you go from the convex side to the concave side of a spherical surface of fluid, which has surface tension T, it creates a pressure difference, an increase in pressure from convex to concave side of 2t by r. Okay. So first you can just go through this part and note down the critical things, and then we will come to the final part of the derivation, where we'll show that why the net force due to that uniform pressure acting on a surface like this, on a hemispherical surface, is equal to pi r square multiplied by the uniform pressure. So it's exactly half times the total surface area into the uniform pressure. So where that factor half comes from? Yes, Ansh, you have a question, Beta?
Sir, can you explain the diagram again? The FBD of half of the spherical shell.
Yeah. So see what is happening now on the FBD of half the diagram. Like imagine you have like a spherical shell of liquid like this. So it's like So imagine you're like, first of all, imagine you're just considering the surface. So there's nothing inside. You have just a spherical shell, and then you've taken half of it. So that half is like this. So on that half, okay, the other half from this side is pulling these with force vectors like this. No? It's pulling it with force vectors in this direction. The surface tensional force. Okay. So imagine, you have basically like suppose you have a very thin, rubber ball which is hollow from inside, and you cut it in half. So you get that hemisphere of rubber. But when it was intact, you could see that the rubber on the other side is stretching and pulling it like this, right? Because of the elasticity of the rubber, especially if the air inside was at higher pressure than the air outside. Got it understood?
Yes, sir.
Okay, so if you take a small length element dl on this circumference of the open hemisphere, that will experience a force vector along the axis. Okay, so those are these red colored force vectors, and that will be T into dl, surface tension into dl. Got it now?
Yes, yes.
So these ones are all parallel. So when we sum them up, it will just be surface tension multiplied by integration of dl. And integration of dl is the total circumference. So that's how that one is coming out to be T into 2 pi r. Whereas now the internal pressure of the air inside the rubber ball, or in this case, there's a liquid inside that liquid shell. Okay, so that liquid is applying pressure, and force due to pressure is always normal to the surface. So any surface element dA, any surface area element dA will experience a radially outward force pointing outwards from the center like this. So those are these vectors, dF vectors. Understood now?
Yes, sir. Yes.
And now the external pressure of P naught is creating radially inward on the outer surface, on the outer part of the surface is creating like this, right? Okay, so that is about the diagram. Now, step by step, we will come to the calculation part. So first is just the formula itself. Okay, this excess pressure is given by this. Now we are coming to the proof of this later. So in the first step of the proof for this formula, that excess pressure is 2T by R, the first step of the proof is you mentally imagine that you are making the FBD of half of the surface. And so the volume of liquid inside the sphere is actually bounded by a thin spherical surface. Now you're imagining the situation of half that spherical surface, how it's behaving in terms of forces. So the liquid inside is applying force outwards on it, which is these dF vectors. The external air pressure is applying a force of dF naught on each of these surfaces. Whereas the other half of the surface is pulling it in this direction with these surface tensional forces. Okay? So now these forces, when we integrate them together, they will become three types of forces. One is surface tensional force, the other is the net force due to internal pressure, and the third is the net force due to external pressure. Right, so far this is clear now?
Yes.
Okay. Okay, so you can just make a note of this part, or I'll just scroll up again a little bit. And then we'll come to the last part, that how we prove that those two forces, the ones because of uniform pressure on a hemispherical surface, actually happen to be exactly pi r square into that uniform pressure. Okay, so there's a very interesting logical way to understand that also, and there's a very rigorous calculus method also, vector calculus method of it, and we will see it by both the methods because it's a good exercise in calculus also, calculus and integration. I mean vectors and integration, both the things, as well as there's a nice logical way to remember it. Okay, so as I was saying, there are two ways of understanding this. Okay, so we'll start with the easy one, which is the logical method. So for that, we'll think of this as a different problem altogether now. Now we'll think of it like if we have a solid hemisphere. Okay, if we have a solid spherical body which we have cut into half, so we've got a solid hemisphere now, okay, and it's in a uniform external pressure field, like it's in, it's on the surface of the earth, so there is more or less uniform atmospheric pressure acting on it from outside. So now consider a solid hemisphere, okay, under the action of uniform atmospheric pressure of P naught, like this, okay, where it is placed like this, that. So what should be the net force due to atmospheric pressure? How much should this be? Should be zero, right? Because if there's no pressure gradient, okay, there should be nothing like upthrust or no net force due to pressure. So this should be zero. Okay. So now consider that all these force vectors that are acting on the hemispherical surface, on the curved part of the hemisphere, they are contributing towards a net force of F1. Okay. And all the forces that are acting on the flat surface on this side, so now remember it's a solid hemisphere, they are contributing to a net force of F2. So this means basically that the two should balance. F1 should be equal to F2, where F1 is the net force on the hemisphere's curved surface, curved outer surface, okay, and F2 is the net force on the flat surface on this side. Okay. Now, out of these, F2 is easier to calculate, okay, because it's a uniform pressure and it's a laminar surface. Okay. So there you go. So that easily proves that the force on a hemispherical surface is equal to uniform pressure into pi r square. So that is why in our earlier diagram over there, the force due to the internal pressure, just the direction of the vectors is reversed, but it becomes the internal pressure uniform value P into pi r square, and the direction is outwards. Okay. And the force due to the outer uniform pressure of P naught becomes P naught into pi r square, like this. So this is a simple logical way to remember this proof also. Okay. Now the other way of understanding this is with proper integration, which is like a good exercise for doing application of integration. It's really too lengthy otherwise, but we'll take a look at the steps of that also. Okay. So now, if we are now, it really doesn't matter whether we are taking a solid hemisphere or a hollow hemisphere, because basically we are going to do the full derivation, provided I can get this. Okay, so now what we'll do is we'll imagine this is the center of this open surface of the hemisphere. So the disk of the hemisphere is, let's say, in the YZ plane, and the x-axis is the symmetry axis. So what we'll do is, taking the symmetry axis, we'll cut a thin ring like you're used to doing in gravitation or electrostatics. Whenever you have to do along the surface of a sphere or a hemisphere or whatever, slice it into rings where the position of the ring is taken by this angle and the thickness of the ring is taken as r d theta, and the radius of this ring becomes r sine theta in my case, and the thickness is r d theta. So the surface area of that ring becomes circumference into thickness. So right from center of mass going through rotation, now electrostatics and all, you're used to this kind of application. Now let's talk about how force acts on that ring due to external pressure or internal pressure or whatever. Okay? So what is happening is, now on that ring itself, if I further slice that ring into sectors, or small sections, and I consider two sections which are diametrically opposite. So on this ring here, I'll take a small area, delta A. And because of external pressure, the force acting on it will be along this line. That will be a delta F naught, which is P naught into delta A. Okay. But there will be one which is diametrically opposite. And on that, equal amount of force will be acting like this. So out of these force vectors, what is the component that acts in the adding direction? Okay, so you can see that for these forces, the delta F naught's sine component cancels, right? Because that's the vertical component, and the cos component adds. So here for the ring, there will be a net force that acts in this sort of direction. So that net force will be pressure into area's cos component, because everywhere the cos component is adding and the sine component is cancelling. Okay, so that will become P naught into 2 pi r square sine theta cos theta d theta. So this is the net force on the ring due to uniform external pressure. So now the net force on the whole hemisphere, this will become integration of this due to the external pressure. Okay, so that becomes integration of this quantity, 2 pi r square P naught over all the rings for the hemisphere. So for all the rings of the hemisphere, theta will go from 0 to pi by 2. 0 corresponding to almost a dot like ring over here, and 90 corresponding to the outermost, the one which coincides with the circumference. So we're left with a very simple integration. Okay, you can just take this as P naught into pi r square sine 2 theta d theta, or you can use a substitution also. that becomes P naught into pi r square. Okay. And same way you do the derivation with the reverse direction of the vector arrows and show that the force because of the internal pressure is horizontal but along the positive x direction. Okay. So I'll just take you through the steps once more. Okay, from here. Oh, Nikita, you wanted to see this part also. So this is a logical way to understand this. So these two delta F naughts here, they are not the force on the entire ring. On the ring, we have taken a small sector or a small section of area delta A and delta A. So from that, we can see that these components cancel and these components add. So now if we add the components for these delta A's across the entire ring, the net force we'll get on the ring will be along the axis of the ring, and that will be equal to this. Okay. And then we integrate for all the rings from theta equal to 0 to pi by 2. So that shows us that it's the same thing that we had logically understood. Okay. So this is an interesting derivation and good sort of way to learn application of vector calculus method. But apart from that, there's nothing to it. You have to just remember the formula for direct application, that excess pressure across a spherical surface or inside a spherical drop is 2T by R. So we'll conclude here. Next time we will see some application questions and also the final part of surface tension, which is about contact angle and capillary rise, and also the final part of non-ideal fluids, which is viscosity. So we will complete viscosity and the remaining part of surface tension in the next lecture. And subsequently after that, we will get a move on into the next section of physics, which will be oscillations and waves, which is very significant and like somewhat more, you can say, has more weightage from your JEE point of view compared to these topics we've done like fluids, etc. They were much smaller topics. Okay. Anyhow, so that's it for today's session, people. Thanks
So
for
can you
attending and
take
wish you all the
fluids
best.
doubts next lecture?
Sorry, Vidam, what was that, Kevin?
Can you take fluids doubts next lecture?
Yeah, okay. We will keep a doubt session maybe for fluids and properties of matter together, right? Okay.
Yes, that's it.
Yes, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Okay, people, bye then. That's it for today.
Thank you, sir.